Hello, ladies and gentlemen. My name is Gunnar Grün and I am the Deputy Director of the Fraunhofer Institute for Building Physics, IBP, and Professor of Building Physics at the University of Stuttgart. Welcome to the third lecture of the LHP module of INDORE. Today we will have a deeper look into the different options to enhance the energy efficiency at the Lighthouse project in INDORE. Today we will focus on the heat loss through ventilation. We will evaluate the influence of night ventilation on the energy demand and calculate it specifically for a housing unit in INDORE. As a first step, let's go back to the basics of energy efficiency in buildings. In module 1.3, we discussed the balancing basics in general. Today, we will have a closer look at the ventilation heat sinks. In INDORE's climate, we have both a heating and a cooling period throughout the year. So we look at the energy balance for each period individually. Here you can see the cooling period, where the sum of the sources from solar and internal gains results in the sum cooling demand. Here we consider the heating period. The only change in the cooling period is that the sinks on the right-hand side are now higher than the sources, which leads to a heating demand. As stated before, we focus today on the ventilation heat sinks. The possibilities to reduce the influence of the ventilation heat sinks was already introduced in the module 2.3 about the Lighthouse project in Rajkot. These were, for example, the use of night ventilation, the implementation of a heat recovery ventilation system, or the reduction of leakages. In this module, we will focus on the aspect of the night ventilation and its influence on the energy demand of one flat at the INDORE Lighthouse project. We will perform night ventilation through natural openings such as windows and doors. To get you started, we will first present the ventilation calculation itself. The ventilation heat loss is calculated using the so-called air exchange rate NL. It indicates how long it takes for the air in a room to be completely exchanged once. The calculation method is the mass flow, as you can see it on this slide. Let's see what this equation calculates. First, we have the material we are looking at. In this case, we consider the air, which has a density of 1.2 kilograms per cubic meter. This material is in our room with a certain volume VL. Now, we want to exchange the air volume through the openings available in the room. How long this would take is indicated by the air exchange rate NL, which is dependent on the available openings and their position to each other. For example, when the windows and doors are closed, the NL value is between 0 and 0.5. When a window or door is fully open, this value increases to 9 to 15. And when opposing openings are opened, the NL value can be as high as 40. Further exchange rates are indicated in the table on the left hand of this slide. With this knowledge, we can now calculate the mass flow of the air in the room in our housing unit in INDORE. Let's start by looking again more closely at the equation. What input data do we need? The first information is the bulk density of the air. The second component is the room air volume, which we look at. The last component is the air exchange rate as indicated by the table on the left-hand side of the slide according to the openings in the flat. For our situation in INDORE, we assume the following values. The air density is 1.2 kilograms per cubic meter. The room volume comprises 48 cubic meters. And for the first evaluation, we assume that all windows and doors are closed, so that the exchange rate is 0.5. This results in an air mass flow of 28.9 kilograms per hour. If the situation of the openings changes, this volume flow also changes, and the calculation must be carried out again. Depending on the indoor and outdoor temperatures, this figure is the basis for the energy transported by the airflow. Let us now consider what influence this airflow has on the energy demand of an apartment. To determine the impact of night ventilation on energy demand, we simulated the apartment with a thermal simulation program. We have assumed here that ventilation takes place through the window during night time in summer. The idea is to use the mass flow of air to lower the indoor temperature in the room during colder night times. In this submodule, we will only look at the results of this night ventilation on the energy demand of the home. The impact of night ventilation on space temperatures will be examined in the fifth submodule of this LHP module. Let us start with a lightweight design without night ventilation. We consider the results for each of the heating and cooling periods side by side. The night ventilation is only used in the cooling period, and the values for heating period do not change. For this construction, we need 22.3 kilowatt-hours per square meter heating energy and 34.7 kilowatt-hours per square meter cooling energy, which results in a total energy demand of 56.9 kilowatt-hours per square meter. Considering the same design but with night ventilation, we find that the cooling energy demand is reduced from 34.7 to 33.7 kilowatt-hours per square meter. The same is true for the heavy construction. Here we have used a different material that has a higher density and therefore a higher conductivity. Here we see that the total energy demand is slightly increased. Both heating and cooling demand is slightly increased, but also the night ventilation reduces the energy demand in the cooling period. Overall, it can be stated: in this particular case, night ventilation reduces the energy demand for cooling by about 3%, regardless of the construction type. However, night ventilation must always be adapted to the season. In addition, the influence of night ventilation can be increased if the U value is reduced, e.g. by exterior insulation. In this case, the total energy demand could be reduced by 7%. And with that, I would like to thank you for watching this video and hope that you will continue the course and dive deeper.